Okay, let's get started. Good morning, everyone. Today, we are going to give a seminar, which is five myths and the misunderstandings in thermal and the chemical reactivity hazard. This webinar will be delivered by me. Usually, my nickname is Tanner, and also somebody call me Guibin, Dr. Zhao, whatever. Okay. Thank you for everyone attending this webinar, and let's move forward. Why it doesn't work? Let me see. Oh, okay. First, give everyone a little bit introduction about me, and I'm Tainer, as I just mentioned. I'm the co-founder of Prime Process Safety Center, and me and Emmanuel, both of us, founded this company. And my previously, I'm working with Wanhua Chemical, and also for DECRA for many years. That's basically is my entire process safety field. The history of my background. So today we're going to deliver this webinar with the following content. First, we're going to talk about a little bit about the background, what is chemical reaction hazard, and how the industry impacted by chemical reaction hazard. And then we're going to share chemical reaction hazard, the fundamentals, how and what is the key parameter that will lead to long-chain reactions, which usually can, lead to like a catastrophic incidents. And then we're going to share five myths and misunderstanding on chemical reaction hazard. This happens in the industry a lot. That's why, I summarize these 5 points, share with everybody. And then I will going to give the summary of, this webinar. And then we probably spend a little bit time, 5 minutes, give a little bit introduction about the Prime Process Safety Center, what we do, and finally have probably 2 minutes about Q&A session. Okay, first background. Probably everybody know, catastrophic incidents has been happened, from chemical reaction hazard, and historically you can say in the following, like 1947, Texas City, here we're in Texas, and but Texas City have a disaster, incident, which is ammonium nitrate cargo detonation. And this is a very bad incident. And I think in 2019, there's another ammonium nitrate decomposition leading to detonation in Europe. It's a very big one. And another one you can say everybody know Bhopal incident, right? So this is thousands of people killed. I mean in India. So in China, I mean, in recent years, there's several big incidents too. One is 2015 Tianjin blast, and in this, port, there's lots of like unstable chemicals stored in there, and I think a major incident caused by nitrocellulose and ammonium nitrate, and this incident caused like 165 deaths, and lots of people get injured, and the magnitude, the consequences like 2.9 magnitude earthquake. You can imagine how huge the impact it is. And also 2019 there's another incident that happened in the Jiangsu province, and this is basically it's a waste chemical storage in a plant. And finally, this explosion basically destroyed the entire industrial park. Not just this company have, just demolished, and also many company around in this industrial park basically demolished. So we can say, later on in this figure, you can see this is the 2019, 2015 Tianjin blast. how bad it could be. You can see these two pictures really bad, and I have some video later on, and and this one is 2019 in in Jiangsu province. So there's a little bit video I want to share with everybody. You can see how bad it could be, by uncontrolled runaway chemical reaction. This happened in Jiangsu province. It's East China. This is like maybe 5-10 miles away, the area. You can see it's it's very bad one, that's from the 2019 incident. You can see these two incidents happened in China. One is in North Tianjin, another one is in Jiangsu province. You can see this is a massive crater in the ground caused by the runaway chemical reaction, and that lead to detonation. I think finally it's a big one. Probably everybody know 2007, in US, Florida, the T2 laboratory also have a huge, runaway reaction caused like reactor burst. That also killed lots of people. And later on, we're going to share more information about this incident. You can see the reactor thickness, it's 3-inch thick of reactor thickness. What's, you see totally like a burst. And this is typically caused by this really a long-way reaction from chemical reaction hazard. So next, let me share chemical reaction hazard as fundamentals. And you can see this curve. We're going to mostly talk about chemical reaction hazard. Actually, in the industry, most chemical reaction hazard can be described by this curve. You can say the vertical axis is talk about energy release or heat removal, but the horizontal axis is talk about temperature. So red curve is represent the heat generation from exothermic reaction. Probably everybody know, heat generation of reaction is the heat generation rate is increased by temperature, mostly exponentially increased by temperature. That's why it's curved like this. However, from heat removal point of view, it's linearly increased with temperature. This is a heat removal curve. And at some point, if your temperature control is well at the curve under here, and then runaway reaction will not occur. But if temperature go higher than this point, and then the runaway reaction will occur. So usually this temperature we call the temperature of no return. So this is the typically runaway reaction happen. You can imagine, for example, if reactor is big, and compare big reactor, small reactor. That means the heat removal, the heat transfer coefficient will shift up and down. So that's why this curve we really like talk about runaway reactions. Usually runaway happen at when dq by dt by heat generation rate larger than heat removal rate. So this is a typical case, okay, for fundamental. Understand this curve and will utilize this curve will help a lot to identify chemical reaction hazard and design system how to prevent this thing happen. For chemical reaction hazard, there is some fundamental, like a testing technology, which can used to characterize, the chemical reaction hazard. For example, for exothermic reaction, how much energy can be released? These fundamental questions we should ask us. And also, like, what's the answer temperature of wrong exothermic reaction? And if wrong reaction happen, I mean, how bad it could be. For example, how pressure will increase with time. Will this pressure caused by vapor pressure or gas generation? So there are very different, by overpressure. If overpressure by vapor generation, usually vapor release, it will suck energy by latent heat. But however, if it's gas generation, there's gas generation barely take energy out. So that's a different sense. And another sense like can be, for example, if long reaction incurred, and from some temperature, how long time you have can handle this situation, can take measures to control like a long reaction. So this all these things like chemical reaction hazard can be identified, can be characterized by the following technology. For example, screening test, something like a differential scanning calorimeter, RSD, this type of testing equipment. For intended reaction, usually we need to use like a reaction calorimeter or micro reaction calorimeter to identify what is the reaction heat for intended reaction. And another testing technology could be like adiabatic calorimeter, something like acceleration rate calorimeter or one season package. Later on, I'm going to share the information with you why these testing are different, what's the purpose for it, and how we should well utilize different tests or combine the test to accurately identify chemical reaction hazard. So for differential scanning calorimeter, this is a typical equipment that we have like a TA instrument for differential scanning calorimeter. Usually differential scanning calorimeter will get the curve like this. The vertical axis is heat flow, and the horizontal axis is the sample temperature. Usually this running at the temperature run about 2 degrees C per minute to like 20 degree C per minute. So as you can see, for example, for this curve, you can see at the very beginning with temperature increase, that this is like a endothermic. Usually show like a, for example, solid is melting. And then later on, once it's fully melted, and then you can see there's an exothermic curve. So we can integrate this area so we can know how much energy it can be released from this reaction. And here we also can get what's the onset temperature of exothermic reaction. But this is DSA, we know the energy level of all chemicals, how much energy can be released from temperature rise. But DSA doesn't give any like pressure information. Another good utilization of DSC, which can use to be identify autocatalytic reaction. For example, for normal nth order kinetic model, usually at the very beginning the concentration of reactive chemical concentration is high. So with time going, so this reaction heat release rate will drop. However, for autocatalytic, chemical at low temperature, it may not have any exotherm, but with time going, and it will have exothermic reaction happen. So this bell shape of curve usually tell us, the chemical can be autocatalytic, chemical. The other one is like a reaction calorimeter. For example, this is like we have THT micro reaction calorimeter, and this can be used to test intended reaction, like how much energy it can be released. And this information can tell, industry, under normal operation, and if, for example, suddenly loss of cooling, how bad the intended reaction could be. This testing, for example, vertical axis tell us the power, meaning one, and the horizontal tell us the time. This run at a constant temperature. This isothermal test. You can say when we inject the active chemical in, and immediately the reaction occur. You can see the heat release. So by integration of this area, so we can get the energy release from the intended reaction. So this is accelerating rate calorimeter. You can say this testing uses a small bone, normally from like about 9 cc volume, and this is temperature, the pressure measurement, deep tube. So we can through here we can measure like the pressure. So this usually acceleration run at HWS mode, heat weight search mode. For example, for this one, you can say red curve is temperature, and the blue curve is pressure, and the horizontal is time. For example, this one we run at 30 degrees C, didn't find exothermic reaction, and then heat to 35, and then to 40, and to 45, and then finally reaction pick up. So that means we can use this, we can detect what's the onset temperature of this reaction. It's about 45 degrees C. And also the pressure increase, we can see how bad it could be. Say the pressure rise at some temperature, it will be very, very sharp. So that means it also tell us what is the maximum pressure it could be. And usually from this temperature curve, we can deduct the reaction kinetics, such as reaction order, activation energy, and also like reaction order, this pre exponential factor. So from arc testing, usually this is adiabatic test, usually will give very good information about long-wave reaction kinetics. But I should mention, since this testing cell is high pressure cell, its mass is big. So usually that means for this test, 5-factor is high. We're going to talk about later on what is 5-factor and how it will impact the chemical reaction hydro identification. So this is the wind season package design recommended by Dyer's program, Design Institute for Emergency Relief System under AICHE right now, and this wind season package used to simulate industrial scale reactor when one reaction happen. What's the results of this? Equipment can be used for lots of testing. For example, for tempering test, for closed cell test, for open cell test, and also for gas generation test. So the function of this equipment can do lots of things. Directly simulate the industrial scale reactor. It's not like ARC, for usually for small scale. So for this example, for example, this is for tempering tests we run for our clients. Use temperature test usually run at open cell condition. We fix the background pressure, and say long wave reaction pick up over here, and you can say at some point long wave reaction will stop because this temperature is constant. That means the heat release rate by vapor generation, heat release rate is equal to removal rate by vaporization. So this is a tempering. Another one is like show like gas generation rate test we did. We can use this pressure information and to get how much gas generation could be, and which is related to reaction kinetics. Chemical reactivity hazard, the fundamental. Next one, we're talking about 5-factor. You see, for any reaction, for any scale of reactor, and for example, we assume A plus B uh, uh, produce a product, whatever it is. For example, in this case, the energy released by chemical, where does this energy go? Usually, for any type of reactor, the energy goes to 3 parts. First part is to raise temperature of reactant. That means the reactor raise the reactant. Second one, energy raise the temperature of reactor itself. And third one is heat loss to the environment. So let's go to next one. Say what is difference? For what is adiabatic? Why adiabatic testing matters in the industry. So this one, the first we should say the first difference of industrial reactor means large scale reactor, and the lab reactor, small scale reactor. What's the difference could be? As you can see, for small scale reactor, heat loss to the environment is huge. So for example, let's give you an example for reactor volume from a 25 cubic reactor volume. And we want, for example, how much time it will take to drop temperature from 80 degrees C, drop 1 degree C to 79 degrees C. How long time it will take. So I did this simulation, by using like the natural vaccine, heat release to the environment, for example, 25 degrees C at ambient, and say how much, how long time it would take. For 25 cubic meter reactor, one temperature degree C drop uh, uh, will take about 4 hours. You can see here. For 12.7 cubic reactor, it will take like about 1 hour. For 2.5 cubic meter reactor, it will take 21 minutes. If it goes to 10 cc, reactor volume, 11 second, temperature will drop 1 degree C. 100 cc, 17 degrees C, 17 second. As you can see, with reactor scale, increase actually heat release to environment will increase, not something. This tell us usually in the industrial reactor, even you do not add any insulation in there, probably it's like adiabatic reactor because the heat release to the environment is so slow. As you can see, 4 hours drop 1 degree C. In our wind sizing package, we just shared with you that testing equipment, it will take 247 minutes. It's also like 2 hours, 4 hours time to drop temperature from, drop 1 degree C temperature. You can say wind sizing package is really representative industrial reactor, for example, at least like 20, 25 cubic meter reactor. That's how this wind sizing package designed for. Okay, this is the first difference. The second difference, let's talk about energy released to the energy was absorbed by the reactor. Let's compare like a big reactor and a small reactor like this. For example, here we have 12 cubic meter reactor, stainless steel 304. It's a material, and the design pressure is 5.2 bar. Mass of reactor could be 6 ton, for example, if we have like reactants, it's like 10,000 kilogram, and we know this specific heat capacity of reaction mixture is like 2.4 joule per gram per K. This is normally for many like organics. It's like this. And let's calculate the heat capacity of reactor. You can see here it's about 3 megajoule per K. What does that mean? That means if you want increase temperature about 1 degree C for the reactor will suck 3 megajoule energy. And if you say for reaction mixture, and this is the heat capacity, so it's 24 megajoule per K. That means if temperature increase 1 K, the chemical can suck like 24 megajoule. If we make this ratio, you can see this how much energy sucked by the reaction mixture, and this is how much this is total energy sucked by the reactor and the reaction mixture. You can see for the energy release from big reactor like 12 cubic meter reactor, almost 90% of energy was contribute to increased temperature of reactants. However, if we go to small reactor, for example, like a 10 cc reactor, usually this reactor is in the lab scale, and the same thing, we consider the same material, same design pressure, like a reactor mass 120 gram, and we do the same thing. You can see here, compare the heat capacity. You can see for small reactor, you for you only have 21% of energy uh, was distributed to the reaction mixture, and the most of energy was absorbed by the reactor itself. So this tells us a very important information. If you run a small scale reactor, you probably will not see much temperature rise in small scale because most of energy contribute to the reactor itself because the heat capacity of the reactor itself is high. However, for industrial reactor, you can say when you scale reactor from small to big, and you can say for bigger scale reactor, you will see the larger far larger of temperature rise than small scale reactor because most of energy was contribute to increased temperature of reaction mixture. As everybody know, for non-win reaction, temperature the reaction rate is exponentially increased by temperature. So that tells us for big scale reactor, the reaction rate would be far larger than for small scale reactor. That's why, many times when people run test or run reaction in the lab, he may not feel much heat, energy release. If you scale up to a big scale, a big surprise will come out. So this is exactly, the incident occurred in Tito lab we just showed you. Okay, so as for, chemical reaction hazard, expert, everybody should, you know, adequately understand the difference between big reactor and small reactor, what's the difference it is. So for the second difference, basically comes to a factor which was called five factor. This is a very important concept. I hope everybody take this concept to home and will utilize in your work. So basically, five factor tell us for exothermic reaction how much energy, total energy release, how much goes to the test reactor itself, how much energy went to the chemical itself. This is definition. Basically, heat capacity of the total reactor and chemical divided by the chemical heat capacity. As you, for a 1 cubic meter glass line reactor, phi is about 1.41, and for 10 cubic meter reactor, phi is equal to about 1.13. As you can see, with reactor scale increase, and the phi factor is gradually close to 1 because when reactor goes huge, this term is almost equal to 0. That means the heat capacity of reactor itself is far less than heat capacity of chemical with reactor scale increase. So for example, let's say for the testing cell, and what is typical, five factor it is. For example, for RST testing cell, five factor is 2.5. For ARC, we just share with 1.5. For wind size and package is 1.05. That's why, we say wind size and package can be directly used to simulate large scale, reactor when runaway happen. This tells us like a five factor how it impacts the reaction parameters. For example, for time to maximum rate, this basically is the time we just shared in like when one reaction happen, how much time you have, you can handle this, and you can control the reaction. If TMR is very small, you barely have time to handle one reaction. That means incident can be easily occur. So you can say for TMR, for high five factor, TMR is larger than low five factor because scale is increased. So the TMR will drop a lot. So that's why that's basically explained to in the lab usually didn't say much wrong reaction, but in the industrial scale things may happen. So this is for dt by dt, temperature rise rate. So low phi is larger than high phi for dt by dt. For adiabatic temperature rise at a low phi reaction, reactor, you probably will say large delta T, temperature rise than high phi factor. And dp by dt and p maximum the same trend. So that's why in the lab, if it's high five factor, for example, since large part of energy was absorbed by the reactor itself, so with time going, long reaction happen, you barely see much temperature because of many energy, much of energy contribute to reactor itself. However, when you scale up to a big reactor, so since in this case, most of energy comes with the reaction, mixture, and then this temperature would be high, maybe at some point will trigger like secondary decomposition of many reactions. So let's talk about the five misses. The first miss, endothermic reaction are inherently safer than exothermic reaction. This is really uh, not the case, especially for some reaction, for example, like some gas acceleration reaction. This is not the case. Be careful, when we talk about endothermic reaction, and I can say for many of them, yes, endothermic reaction is much safer than exothermic reaction if there's no gas acceleration. However, if there's gas acceleration, this can be total turnaround. Let me share an incident investigation we did for a company. You can say this company used Pennyman reactor to make pigments. So you can see there's so many incidents occurred in 3 years. And then we did the test, arc test. You can see from arc test, this temperature curve, you barely see much exothermic reaction. And when one reaction happens, this reactor run basically at about 80 degrees C. It's 70 to 80 degrees C. You can see in this temperature range, you barely see much, exothermic reaction happen. But this instance, you see that this is basically ion nitrate decomposition. Ferrous nitrate decomposition will generate lots of logs. It's a big, and like a environment damage incident. However, when we do further tests, since you can see from our test, this is barely like exothermic. And when we run more tests in the RSD, we found this reaction basically is autocatalytic reaction at different pH value, and then we said time to decomposition is change when we fix the temperature. But even for the same pH value, for example, like here, like 1.9, when you change temperature and the time to decomposition is also change. So this tell us really at this situation, this is autocatalytic reaction. So for first misunderstanding, okay, when you talk about endothermic reaction, watch out the gas generation. Okay, that's a point to take to everyone. The second one, if onset temperature is 50 degrees C higher than my operation temperature, my process is safe. So this is also we need to be careful. First, we need to understand the concept of onset temperature. So onset temperature basically is the temperature at which a reaction can be detected under the prevailing heat loss and five-factor condition of the test. For example, DSC test tell us onset temperature. It's different than onset temperature when we run in the ARC test, and also which is also different than zero onset temperature in the Venn package. So when we talk about onset temperature, we really need to say what scale of reaction you are running, and do you have heat loss to environment or not? Okay, so that we need to well utilize onset temperature this concept. That's what I say. For given reaction, it is equipment dependent. It's not a constant, and normally coded as a temperature at which the rate of self-heating exceeds a threshold. As you can see, for the detection limit of exothermic reaction, our case is usually like 0.02 degrees C per minute. But like for Venn package, it usually is 0.2 degrees C per minute. But even like that, five factor will impact it too. As for example, this one is we calculate based on the how five factor impact the onset temperature of reaction. For example, Ta0 is T onset phi equal to 1 with change five factor for different activation energy of reaction, the onset temperature change a lot. So that's why when we talk about 5 degrees, we really need to first ask us how you did it, how you get the onset temperature, what scale of testing or like industrial scale you're using, and we need to make it clear. Otherwise, we're going to make a big mistake. So the concept, so usually, I mean, if we want to use the concept of onset temperature, we really need to think about, some safety factors before we use. For example, for screening tests like DSC test, usually say we probably need to take like a 5 to 100K, and then not just the 50K. If we want testing in adiabatic test, it maybe something can be 10 to 50K. Really depends on 5 factor, and also the scale of the activation energy of the reaction itself. So in this way, so when we use onset temperature, we say always apply a conservative factor, safety factor, to account the like a kinetic deviation by different reactions. And also be careful, auto-catalytic reaction, it can be very different, as we just give an example before. So otherwise, small scale reactor behave the same as full scale. This is a big mistake. Okay, small scale is totally different than big scale. For example, let's watch out this T2 laboratory incident. You can see this very big incident, and let's say you say when long reaction reactor burst a big. This video is from civilian camera taken by US and and it's really like a mushroom, you see, the reaction. And this is the surrounding area was damaged. Let's look at the video of this T2 laboratory incident. It can be you can find from CSB, and basically CSB made this video.
T2 produced MCMT, a gasoline additive, in batches using a 2,500-gallon reactor. An operator controlled the process with a computerized system in a nearby control room. In the first step, liquid chemicals and sodium metal were loaded into the reactor, heated, and then mixed with an agitator. The reaction produced hydrogen, which was vented to the atmosphere. In normal operations, when the temperature reached 300 degrees Fahrenheit, the operator would turn off the heating system. But because this reaction was exothermic, or heat-producing, the temperature inside the reactor would continue to rise. At 360 degrees, operators would begin to periodically fill the reactor's cooling jacket with water. As the water boiled, heat was removed, controlling the temperature. However, on the day of the accident, the CSB found that the operator tried to cool the reactor as usual, but the cooling system likely malfunctioned, perhaps due to a blockage in the water supply piping or a valve failure. The temperature and pressure inside the reactor began to rise uncontrollably in a runaway chemical reaction. T2's co-owners returned to the plant after a worker called to report the cooling problem. While one owner searched for the plant mechanic, the other went to the control room. Concerned about a possible fire, he warned employees to move away from the reactor. Inside the reactor, the pressure was still increasing, reaching 400 pounds per square inch and boosting the rupture disk. Witnesses heard a sound like a jet engine as high-pressure gas began to vent from the reactor. But it was too late. Within 10 seconds, there was a massive explosion, equivalent to about 1,400 pounds of TNT. The blast damaged buildings over 1,500 feet away. Debris rocketed up to a mile. The co-owner and the operator in the control room were killed. 2 operators further away died from flying debris. 32 other people were injured, including 28 at nearby businesses.
This you can say this T2 laboratory, big reactor, normal reaction, how bad it could be. As there's lots of background for this incident. Actually, the two chemical engineers, the owner of these two chemical engineer, they are chemical engineer, and when those scale up, they directly from 1 liter reactor to this big like 10 cubic meter reactor, and they during normal run, usually they observe the temperature is very hard to control. Why? Because they use the same, heat capacity, like a heat remove capacity, and the scale up issue. So usually that's what we say, when we run small scale and big scale, we really need to think about it. What's the difference between from a small container or big container, what's the difference? This is the same curve as we shared at the very beginning. This is the normal reaction heat release rate. And this, for example, at a different scale, basically the slope will change. With reactor size increase, this slope will drop. That means you have less and less heat capacity, the heat removal slope. So at some point, that's why any reactor, the scale up, there's a maximum limit. You can, when you scale up to too big, and if you cross this critical temperature, the reaction will run away, no matter whatever you do. So that's why, for when we say small scale and big scale, they're very different. Carefully analyze this type of, features will help us design, an inheritance safe reactor. Okay. The other sense is like reactive had only matter in a batch process. Actually not, right? I will give you example which is continuous process. For example, this is the reactor one with two flow or stream flow in the reactor, and there's a heat exchanger and continually, recirculate to remove the heat generated, and then there's a continuous, mass flow out. This reactor, the final scenario is like tube rupture, and the incident caused like finally the reactor was burst. So this is a really bad sense. And we did lots of investigation in the detail. And for tube rupture, and we calculate, for example, when tube rupture, how much the water can be flow into the system. And this one is typical. This one is like a, reactive reactant, chemical A can we found chemical A can be catalyzed, decomposed by ion, pollution in the ion you know the water from cooling water stream. So this one we did not work. For example, for RC1 test, we show this reaction. Actually, it's not much energy release. Adiabatic temperature rise is only about 40 degrees C. And from arc, we can say also this is like a weak. It's not very much energy release. From arc, we can say also about 44 degrees C temperature rise. However, this have lots of gas generation, and one more of A can generate basically one-third more of gas. This is what it is. And we recommend clients to do lots of things. For example, how ion concentration will impact the reaction kinetics. This is how it go. We did 0 ppm ion, 10 ppm, 20 ppm, and 50 ppm, 100 ppm. Finally, we got the curve like this. You see, the reaction rate constant, how it changes with ion concentration. When ion concentration less than 50 ppm, its curve shows like linearly change with ion concentration. But over than that, it's impact. It's flattened. But at least for ion concentration less than 50 ppm, we can get this reaction kinetic. How component A decompose with ion concentration change. So we utilize this to do dynamic simulation, to simulate how in the cooling water and when heat exchanger tube rupture, how this will impact the ion concentration, mass balance of A. Finally, we put this information combined with the reactor mass balance from ion concentration, component A concentration, how it change, and finally got a gas generation. And from this dynamic simulation, and we found that actually this reactor, for example, in about this is time is in hour, this is pressure. You see here, in about 6 minutes to 12 minutes, the reactor will be overpressurized because this design pressure, the reactor design pressure is about 3.5 bar. You can see here. So that means that when heat exchanger tube rupture, very quick, 6 to 12 minutes, the reactor will burst. So this exactly found the issue. This just give you an example. Reactive hazard is really for continuous reaction, it can have very bad thing to happen. We have to identify the hazard and know what is unstable, what kind of contamination will impact, stability of chemical, and that's very critical. So Miss 5 is like I say, if we haven't never have a problem, there isn't a hazard. Let's look at the incident happening in the shell. I mean, this video is very interesting. Okay.
On the evening of June 3rd, 2014, two major explosions and subsequently a fire occurred at Shell Moerdijk petrochemical plant. The explosions could be heard within a 20-kilometer radius. Debris from the explosion was found 800 meters away. Two employees were injured in the explosion. The Dutch Safety Board has investigated this accident. At the plant in Moerdijk, Shell produces chemicals from oil and gas. In this installation, ethane and benzene are used to produce styrene monomer and propylene oxide. These products are used in styrofoam, food, cosmetics, and pharmaceuticals. In May 2014, this part of the MSPO2 plant was closed for scheduled maintenance. The main purpose of this pit stop was to replace the catalyst pellets in two reactors with a new type. The catalyst pellets plus heat accelerate the reaction of fluids and gas that are mixed in the reactor. Evenly spreading of liquids across the catalyst pellets is essential to dissipate heat from this reaction. Located below the two reactors are separation vessels which separate fluids and gases. Excess gases are vented to the exhaust gas system. At 8:15 on the evening of June 3rd, operations started to allow circulation of ethylbenzene and nitrogen in the unit as part of the startup procedure. After 45 minutes of stable circulation, the operators began at 8:56 heating the unit up to its operating temperature. They noticed ethylbenzene fluctuations in the separation vessels and in the flow to the second reactor. At 9 p.m., the operators felt that the reactors were not warming up fast enough. They manually increased the heating of the ethylbenzene. This caused the temperature to rise above normal levels. However, operations did not intervene, as fluctuations in both fluid and temperature levels were quite common during startup. The Dutch Safety Board has concluded Shell considered fluctuations of this kind during startup to be quite common. In the course of the last 35 years, Shell did not always systematically examine the impact of plant modifications and replacements based on a risk analysis. Shell, as well as the regulators, failed to identify this. Secondly, important information known at the time of the unit's design was lost, and thus not available for its eventual management. Because this loss went unrecognized, risks arose which Shell Moerdijk failed to control. At around 10:16, an automatic protection system was triggered that was designed to prevent liquid from entering the exhaust gas system. When the flow to the second reactor is reduced, the fluid level in the second separation vessel drops, but the valve remains closed. As a result, the gases in the system could no longer be released either. At 10:48, both the pressure and temperature had risen above the maximum level. The new catalyst pellets caused unexpected reactions. The high pressure reduced the flow of ethyl benzene through the reactor, and therefore heat from these reactions could not dissipate. The heat buildup causes hotspots that accelerate new reactions, a so-called runaway. The pressure rose very fast, too fast for the emergency relief valves. In 2 minutes, the pressure in reactor 2 rises to 180 bar, more than 25 times the normal pressure during startup. The increased pressure causes reactor 2 to explode, followed 20 seconds later by the separation vessel of reactor 1. The ethyl benzene starts a raging local fire. The explosion and the hot burning catalyst pellets.
Okay, that's the incident that happened, in the show. You can say, after this incident, basically the entire plant and lots of area was burned down. I mean, this is a very bad incident. But the main take up is like you can say for this plant, in 1977, at that time probably the technology for chemical reaction hazard identification is not that advanced. So you can see when they do it, they warm up isobenzene with catalyst and like use at that time it's like about 130 degrees C. But after that, they didn't do much, since. And then they continues, running this type of thing. They improve catalyst, and the catalyst probably becomes more active. But after that, nobody think there is an exothermic reaction between catalyst and isobenzene. And that's caused this incident. You see, this unforeseen chemical reaction hazard occurred. Actually, this also have lots of gas generation. So basically, this lesson tell us, if you have never done chemical reaction hazard in your process, please do it. Otherwise, you think you're safe, but there's no data support your conclusion. It may comes to like some incidents. You see, this incident happened in the 2014, from 1977 to 2014. How many years? Almost 40 years passed and no incident, but all of a sudden a big incident occurred. This is a big hurdle for the shale. Okay, this is the main take. Okay, let's go to quick summary. Uncontrolled lung reaction can lead to a catastrophic incident. We see lots of incidents occur, globally, and identify chemical reaction hazard is really a challenge, but it's doable. I mean, by specialized lab and well-trained engineer, and the chemical reaction hazard is very complicated. Sometimes, do a right test and the good understanding what data mean and how can it be used in the design and in the operation is very critical. So misunderstanding or misinterpreting the data or the hazard really can result in incident. Okay, that's a main take, from today's webinar. So, okay, due to time limit, so I will not spend much more time on introduce our process safety center. I think many of you probably know and also go to our website when we provide major process safety testing and consulting and training service. We have a combustible dust testing lab, flammability gas liquid lab, and also we have chemical reaction lab. We have tons of different type of reaction calorimeter, and also we do electrostatic testing and regulatory testing. So our lab is the ISO accredited lab, and basically that's you can see this all these are our equipment. I will quick go through this. And this is the consulting service we provide DHA, HSA, ignition source analysis, and we also provide direct technology service, for effluent handling or vent sizing of long reactions. So and also we provide incident investigation, help clients. So this is training service. Basically, that's all.